the thing that has attracted a lot of attention and gotten a lot of us in the project very excited as well is that when we combine the measurements from DESI with measurements of the cosmic microwave background, and when we combine our measurements also with measurements from type 1a supernova studies that have perform an independent measurement of the expansion history, we find some kind of interesting hints that maybe the dark matter or dark energy model is not the cosmological constant after all.
Greetings. I'm Yvonne Stapp for Science for the Public, and I welcome you to our Contemporary Science program today as a GBH Forum Network webinar. We will hear today about the much anticipated first-year results from a 5-year survey by the Dark Energy Spectroscopic Instrument, better known as DESI. DESI will create the largest 3D map of the universe ever produced and will measure the expansion history of the universe with unprecedented precision to determine the effect of dark energy on the structure of the universe. Our guest, Paul Martini, professor of astronomy at Ohio State University, has been involved both as instrument scientist for DESI and in the research itself. He'll tell us why dark energy and the expansion of the universe are of such interest and importance, and what the DESI project, has revealed so far. Dr. Martini, welcome, and thank you very much for joining us today.
Thank you very much for having me. I'm excited to talk about DESI and about
I bet you are. Okay. All right. There's a lot of excitement around this project, but we need to start, if you would please, with a little background on dark energy. What is it? Why is it such an important thing?
Yeah, the really fundamental question that motivates so many of us involved in the DESI project and in cosmology as a field is to try to understand what the nature of dark energy is, because it's something that is outside of our current understanding of physics. It is quite simply very strong evidence that our understanding of the universe and of basic physics is incomplete. And this is the best clue we have that how we can try to understand what the nature of this missing component could be.
Okay. And what does dark energy do, and how much of the universe does it account for?
Well, dark energy was discovered because of the accelerating expansion of the universe. So as I suspect many people have heard, the universe is expanding because of the original Big Bang explosion that basically produced the universe. And that expansion was expected to slow down over time because of the matter in the universe pulling on all the other matter. And so we know gravity attracts. And so we would expect that the universe's expansion rate would gradually slow over the past approximately 14 billion years since the Big Bang explosion occurred. And that is what happened for about the first half of the universe's history. But about 7 billion years or so ago, we observed that the expansion rate started to speed up again. And this is a big mystery. The universe seems to be defying gravity in that it is now accelerating in its expansion rather than slowing down because of the gravitational pull of the matter in the universe. And this accelerating cosmic expansion this is a mystery. We don't know what is causing it. And the explanation that people offer for it is that there is some dark energy component to the universe, but that's really putting a name on a phenomenon rather than explaining really what is happening. It's more of a description, and we would love to understand physically what it is about the universe that is causing this increase in the expansion rate, this acceleration in the expansion rate.
So it doesn't leave like special particles for you to identify or anything like that so far, right? It's still a mystery.
That's right. It's still a mystery. It could be some aspect of particle physics that hasn't been worked
Yeah.
out yet. There are lots of ideas, lots of theoretical ideas for what could be going on. And our hope with the DESI experiment and with other cosmology experiments is to measure this change in the rate of the expansion of the universe well enough that we can test and potentially rule out or rule in some of the theories that exist.
Okay. Now, can you tell us also some of the ways before DESI, we'll get right to DESI, how DESI is looking at this, but other attempts have been made to investigate dark energy. Could you give us a little background on that?
Sure.
Do like the space telescopes look for it and so forth? Yeah.
Yeah, so the tool that many projects use to try to understand the expansion history of the universe and understand the properties of the universe as well, like how much matter is present in the universe, is measuring something that's called the distance redshift relationship. And so distances are straightforward to understand, is really how far away something is. Although in cosmology, because the speed of light is constant and things are very far away, when we observe distant objects, we are observing the universe as it was a long time ago. So when we observe an object that is several billion light years away, we're really seeing the universe as it was several billion years ago. And when we combine that with information about the redshift, which is a measurement of how fast that object is moving away from us, then we see how the expansion rate of the universe has changed over time. And the real key to most cosmological studies is to measure distances really precisely so that we can track how the universe's expansion rate changes over time. So for example, if the universe had no dark energy component in it, then we would have expected the expansion rate to continue to slow down over time. And that's something that we could measure, and that makes very specific predictions for how the expansion rate should change as a function of distance. And we see a very different relationship in our data, and many experiments have seen this as well, that indicate this accelerating expansion. And some of the first work was done with what are called type 1a supernovae. So supernovae are explosions of stars. They produce extremely high luminosities for a very short periods of time. And these explosions have a well-calibrated relationship that lets us take their observed properties and turn them into a determination of their intrinsic luminosity. And if we can measure how bright something is and we know what its intrinsic luminosity should be, we can determine what its distance is. This is a standard candle, but it is a method for determining distances. And several teams in the late 90s used this method to discover the accelerating expansion of the universe. And then that has been extended with observations from the Hubble Space Telescope and now with the James Webb Space Telescope to get ever more precise measurements of many objects, and also to try to get a very, very precise measurement of the local expansion rate of the universe to measure what's called the Hubble constant, which is the expansion rate of the universe, but in the very local universe.
Okay. Now, but DESI, I'm not even clear here on this, like that, like the Hubble, the James Webb, it's wonderful. They're out in space. That's supposed to be an advantage and so on. And what DESI is doing this from the ground, observational telescopes, but DESI has collected much more data all simultaneously, if I understand it. Is that correct? Like 5,000 galaxies at galaxies, excuse me, at a time. It's huge. Whereas, is it clear that other kinds of telescopes can't do that? Is that one of the advantages? I'm not sure.
That is definitely one of the advantages. So the key aspects that come from space-based observatories, and so as you said, DESI is a ground-based facility, and I can describe more about DESI in a moment, but the space-based facilities, because they're above the Earth's atmosphere, they let us do two things. One is they can provide us with generally much higher angular resolution and consistently higher angular resolution than we can see from the ground when we have to look through the turbulence in the Earth's atmosphere. There are ground-based methods that do allow us to get very high angular resolution nowadays, but the space-based observatories can produce this consistently. And this is particularly useful for experiments like measuring the local value of the Hubble constant, which relies upon measuring very faint variable stars in very distant galaxies and separating their light from neighboring objects. The other thing that being above the atmosphere gains us is that it allows us to observe at a broader range of wavelengths than are accessible with ground-based observations, because our atmosphere absorbs UV light, which is a good thing. It also absorbs a lot of infrared light, but that wavelength range can be really valuable for studying a lot of extragalactic objects.
Right. Okay. Then the next thing is, well, so how does DESI work? What's such a big deal about a spectroscopic, instrument like this?
Yeah, so the DESI project, the Dark Energy Spectroscopic Instrument, is a huge project of over 900 scientists, and I'm just one of those 900 plus individuals that are working on this. So I do want to emphasize that there are a lot of people working on this, and I am fortunate to be able to collaborate with some really brilliant people on this project. We have also over 70 institutions around the world working on DESI, and the project is supported and operated by the Department of Energy's Office of Science, and we're really grateful to them for making this project possible. It has been a huge effort to build DESI, and it's partly it's not in space because it's such an enormous experiment. It would be difficult to launch something this complicated. As you mentioned, it is a multi-object spectrograph, and that means that it's able to take multiple spectra at a time. So it's a good name. It can observe 5,000 spectra at a time. And with the DESI instrument, we're able to observe over 100,000 objects in the course of a single night. And we routinely observe maybe even 1 million objects every month. So it's really phenomenal. And that's a big step forward from previous experiments that took many years to obtain a similar number of observations. And so DESI, even after the first year of operation, has obtained more spectra of extragalactic objects to map the universe than all previous such experiments put together.
Oh, wow. And it's just beginning, really. But the other is what they're focused on is it's galaxies. Is that correct? The big chunks of galaxies. And in terms of the observable universe, how much is this covering?
Yeah, so the DESI
Yes,
experiment is observing over the course of the 5-year survey that we have presently planned, we plan to observe about 40 million galaxies and quasars. So quasars are also a part of our data set. And we are observing galaxies from the relatively local universe out to up to 11 billion light years away, or so 11 billion years ago. So we're observing over most of the history of the universe.
That's it. And just could you clarify what is a quasar? Why is that important for you to use quasars?
Yeah, great. Quasars are among my favorite.
I know.
I got excited about astronomy in the first place from studying supermassive black holes, and quasars are supermassive black holes that are accreting enormous amounts of matter from their surrounding environments. The black holes that power quasar activity can be accreting as much mass as the mass of our entire solar system in a single year. So it's an enormous amount of mass consumption, and they produce light that can be hundreds of times brighter than the galaxy in which they reside. And the reason why they are so valuable for cosmology is because they are just really luminous objects. And therefore, we can observe them across basically the whole history of the universe. So even if they're 11 or 12 billion light years away, we can still see quasars with a reasonable amount of observation time.
I'm not an astronomer, but it seems to me that this is really critical, that if you have the quasars, you really have an advantage that you would not have at all. It would really complicate things if you didn't have the quasars. But is that true or no?
No,
That
you're
sort of
exactly
really,
right. So the
okay.
quasars are hundreds of times brighter than typical galaxies. And so if we want to study the distant universe, it's a lot easier to study quasars because we can observe them more quickly. The only disadvantage of quasars is that there are not enough of them. So get a really dense sampling of the structure
Yeah,
of the universe,
right.
and where we can get a lot of our cosmological information. We can't use just quasars. And
Yeah,
actually, one thing
right,
that we
right.
can do with quasars, though, is that if they're at high enough redshift, we can look at the distribution of neutral hydrogen in the universe along the line of sight to the quasars, because that hydrogen will observe some of the quasars' flux at very distinct wavelengths, and that gives us more information about the matter distribution in the universe. So
That,
quasars can kind of do two things. They can both help us get a window into the high redshift universe at all, but then also to map the matter distribution along our line of sight to that particular quasar.
that's very good information. Thank you for that. And then, in terms of what data has been collected so far, there's all this excitement, a number of articles out there now about this, just the first year. So, what does the data tell you so far about the dark energy and the expansion of the universe?
Well, the data we've collected so far, as of about a month ago, we published a series of papers based upon what we call our first data release, which is based upon analysis of our first year of observations. And that data includes about 6 million spectra of extragalactic objects, covering a pretty large fraction of the sky that we're able to observe from Arizona, which is where the DESI experiment is located. So we're using the Mayall 4-meter telescope that is sited with the Kitt Peak National Observatory that's near Tucson, Arizona. With these data, we're able to map the expansion history of the universe over the last 11 billion years with really unprecedented precision. We're able to measure the expansion history with a precision of about 0.5%, which is a significant improvement over previous work. And we are able to measure this. The technique that we use is something called baryon acoustic oscillations, or the BAO scale. And this is a standard ruler that we are fortunate to have based upon the physics of the early universe that established a slight overdensity of galaxies at a particular physical separation that has stayed constant over time. And what we measure in DESI is we measure the angular size of this feature at a range of different redshifts. And we use the angular size of that feature to determine the physical size of that feature, and thus the distance of that feature at all sorts of different redshifts, and map out the expansion history that way. And what we find with that is we find actually very good agreement with the standard model of cosmology, which is called lambda CDM. So lambda here is the Greek letter lambda that astronomers use to refer to the dark energy component. And then CDM stands for cold dark matter, and that's the matter in the universe. It's primarily cold dark matter. A small fraction of the matter is what we would call normal matter, which is what we are made of, what the Earth is made of, and so on. But then there's also a large fraction of dark matter in the universe that, incidentally, we also don't understand.
Just by the by, right? Right. Okay. So then the results that everybody's so excited about here, they suggest that the rate of expansion has not changed, or it has changed. What does it say?
Right. So our main result, based upon the analysis of the DESI data alone, show that the expansion rate has been accelerating in very good agreement with the lambda cold dark matter model, which is the standard model of cosmology that we have had for quite a while now. The thing that has attracted a lot of attention and gotten a lot of us in the project very excited as well is that when we combine the measurements from DESI with measurements of the cosmic microwave background, and when we combine our measurements also with measurements from type 1a supernova studies that have perform an independent measurement of the expansion history, we find some kind of interesting hints that maybe the dark matter or dark energy model is not a cosmological constant after all. So we find some evidence that we're still working on the significance of that does not quite agree with the lambda cold dark matter standard cosmology measurement. And it's not of such high statistical significance that we're ready to make any strong claims, but it is at the level where we really want to go back and analyze the additional data we've collected since we produced these papers, and we really want to also encourage other groups, and I know other groups are really studying deeply their data as well to try to figure out what's going on. Because if it would be super exciting if we found evidence that the dark energy component was evolving in some way, because there are a lot of models that exist out there that make predictions for changes over time. And if we could actually find that one of those models was a better match to the data, that would be super exciting. We're not at that point yet, but we're very motivated to analyze the additional data we've collected to see if we can make some more statistically significant statements.
Right. Oh, Dr. Martini, what does it mean if the universe is not expanding more, or it's expanding on average like this forever, or if it stops expanding? What's the significance there? What does it mean?
Yeah, so if the dark energy component is not a cosmological constant, but is instead explained by some other type of model, like, for example, there are a class of models within particle physics that are called thawing models, where the dark energy component would be changing over time, then that would provide some evidence that maybe this is actually the explanation for this mysterious dark energy component. I would say that in contrast, the cosmological constant idea, where the dark energy component is fixed, is based upon, or at least one of the physical motivations for that is that it's due to vacuum fluctuations in space. And so simply this component becomes more prominent the more volume there is in the universe. Although the attempts to actually use what we understand about quantum field theory and understanding really the small scale structure of the universe well have not been able to reproduce the magnitude of the effect that we would need in order to explain the accelerating expansion, and actually by a huge number of orders of magnitude. So there's a big mystery there.
Okay. Now, you're going to have 5 years of data down the line here. Do you expect big changes then would this alter your evaluation about the expansion of the universe as you accumulate more data?
Yeah, so we actually just recently finished collecting 3 years of data. So we've recently marked the third year of data collection. Actually, we started the survey, I think, more or less exactly 3 years ago today. And
done the first analysis. Okay. Yeah. Okay.
So it takes some time after we collect the data,
right,
do all the analysis and prepare papers for publication. But yeah, as of now, we have about 30 million galaxy and quasar spectra. So that's about 5 times as many spectra as went into the year 1 analysis. And there's a whole team within the project that work on processing these data into final calibrated spectra and then produce catalogs that we then analyze. And that team is hard at work now on preparing catalogs so that we can conduct a similar analysis, but now using about 5 times as much data as we had for these recent papers. And because of all the excitement around the year 1 results, the results from last month, there are a lot of us in the survey that are really eager to just start analyzing this year 3 data set as soon as we possibly can.
So you do expect possibilities of change there as you accumulate the more data,
Yes.
I should say, analyze more data.
Yes, as our next analysis will include many times the number of spectra in our current sample, and so we expect the uncertainties in our measurements to go down by a significant amount.
Okay. And finally, we're running low on time here, is what's next then for the DESI scientists? You're very busy, so you gather up this data. They gather up the data, but it takes a long time, evidently, to process, to investigate, and do all of that. So you're going to be very busy. But what's next?
Yeah, it certainly takes a lot of time for us to not just analyze our data, but then also to do lots of tests to really make sure that our analysis is robust. But we are certainly planning on our future analyses, and some of that will be analyzing the full 5-year data set that we plan to collect. And so we still have 2 more years of data collection ahead of us. And then we're also proposing to extend our survey for a few more years to get a larger area of the sky, as well as to observe the same area a little bit more deeply, and to collect additional spectra so that we have a basically more uniform coverage of the survey area. Farther afield, we're really excited to conduct a new survey, something that we're calling DESI 2, which would be a survey that was primarily focused on the high redshift universe, meaning redshifts where, well, time, basically looking at when the universe 8 billion years ago and even more distant. So I would say the current DESI experiment mostly focuses on the universe over the last 8 billion years, although we do have some data that goes farther back. But this new survey DESI 2 would primarily focus on even greater distances. And what we're hoping to study with that survey is to try to understand what's called primordial inflation, and the initial acceleration of the universe that occurred right after the Big Bang explosion. And so planning what that experiment could look like, coming up with a detailed proposal that we can use to bring that survey to fruition.
That is interesting. Well, you're going to be busy for a few years, I think. Here,
I hope so.
but and will all the DESI projects then will be focused on dark energy? Is that correct?
So I would say that the primary focus of our current experiment, DESI, is on dark energy, and the new project DESI 2 will be more focused on the physics of the early universe, so trying to understand initial inflationary period and some other aspects of kind of elementary particle physics that we might be able to explore and might have left some residual signatures in the distribution of galaxies in the very early universe.
That's fascinating. So this is wonderful. Thank you ever so much for giving us all this information. And in our remaining time here, we'll take a few questions. We have one up here, and we have a couple more. If I may, let's see. If the project, if DESI looks at objects from the past, is the expansion taking place part of how the universe progressed, or is the expansion including now in real time? So you're looking in the expansion taking place part of how the universe progressed, or is the expansion happening now? Are you measuring a now?
Our observations are actually don't do a great job of measuring the expansion in the very local universe. We are much better at measuring the expansion history from 11 billion years ago to within the last half of a billion years or so. And the reason why we don't do as good of a job in the very nearby universe or in very recent times is simply there are a relatively small number of galaxies in our sample that are very close by compared to the distant ones. And that's because we basically look at we're observing a cone, an area on the sky that's kind of like a cone, and there are always many more distant objects than there are nearby objects.
Aha, it's interesting. Another one, could you explain a little bit more about the lambda CDM theory, how that works because most people are not well versed or don't have a background in that subject, lambda and CDM theory.
Yeah, so the lambda CDM model is a model that combines cosmic acceleration as explained by a cosmological constant with a model for cold dark matter. So the cold dark matter model has existed for a long time, and that's basically a model that just describes, or one of the things that it describes is how the matter distribution in the universe affects the cosmic expansion history. And the idea there is that the more matter there is in the universe, then the more the expansion rate will change over time. It makes many other predictions as well about things like the relative concentrations of different amounts of mass in the universe, and some of the detailed appearance of the conglomerations, or what we call halos, of dark matter that are the seeds for galaxy formation. There are many other aspects of it as well, but for the point of view of cosmology and particularly the expansion history, it's the impact on the distance redshift relationship that I'm most focused on. And then the lambda component is a description for how the expansion history, or is a parameterization that describes how the expansion history would change over time as the universe grows.
Does it predict the change over time? So over these billions of years, and this is not something that's in a bubble, so to speak, but it is the universe itself. Does it predict that well? This expansion.
I would say it is a good phenomenological description of what we observe.
Okay. And is there a necessity for that expansion? Is there a reason why that should be there, that expansion? Why not just stop at some point?
Well, so we have a model description of the expansion history that includes both this acceleration component and the matter component. And that model then makes a prediction as well for how the universe's expansion rate should continue to evolve over time. Basically, the acceleration should continue to increase. If it were to stop or otherwise change very abruptly, then that would require just some additional component to the model that we don't have any data to support just yet.
Okay, because at one time it did, right? Earlier in the universe, it slowed down and then it started up again. And I thought that was a mystery in itself, but no.
Oh, so yeah, there's maybe a subtle aspect of this that I didn't describe well. The measurement that we make in the current universe of the dark energy component and the matter contribution, those a lot of the time when people describe them is in terms of what the current matter energy density budget is in the whole universe, where about 70% is in the dark energy component and about 30% is in the matter component. But that's the component in the universe today. If we look back in time to earlier in the history of the universe, the matter contribution was much larger than the dark energy contribution. And so the relative importance of the dark energy and the dark matter contributions, they have changed over time, even though the dark energy contribution is consistent with a cosmological constant. It's constant in time in a way that's independent of the change in the scale of the universe, whereas the matter contribution depends upon what the density is. And so basically, as the universe gets larger over time, then the matter contribution the density of the matter contribution goes down because the total amount of mass in the universe is conserved. So if the universe grows by a factor of 2 in size, then the density will go down by a factor of 8.
Okay, one more thing. Does the expansion tell us anything about the future of the universe as to whether it will stop and collapse or keep on going forever? Does it tell us anything like that, predict?
Yeah, so the lambda CDM cosmological model predicts that the universe's expansion will continue to accelerate this time.
All right, forever and ever and ever. So, okay, well, that'll keep you busy for a while, yes.
Lots more space.
One more real quick thing here is about the data. Do you know, like in the Large Hadron Collider, you have to throw away most of the data. You can't, there's no place to keep all this data. Do you have the same problem with this kind of data? That you can't save it? Do you have to sort of have a trigger mechanism to select what you're going to save, or is it's all saved?
We're able to save all of our data. So it's a lot of data. It's definitely a big data field. We collect, many tens, if not hundreds of gigabytes of data per night.
Yeah.
But our total data volume is still not pushing the boundaries of technology.
Okay, that's interesting, and that it means it's going to be keeping people busy because that's a lot of data to plow through then. In any case, Dr. Martini, thank you ever so much. It was most interesting to talk with you, very informative, and very good luck to you in the future with this.
Thank you very much. Thank you for having me. It was a great pleasure to talk about cosmology and dark energy and the DESI project, and I had a great time.
Thank you. Bye-bye.